Hi, today I will talk to you about our paper discovering stable periodic frequent patterns in transactional data. This paper, the goal of this paper is to find some patterns we call periodic. Patterns means something in your data that will always repeat over time, that is periodic. So for example, if we look at the transactional data, we mean like shopping data, what do people buy, the transactions. Maybe we find that some people every weekend will buy the wine, the cheese, and so on. So this paper is about analyzing data to find something repeating that could be interesting. Maybe it can help us to take some decision or understand the data. Okay, so if we want to find something periodic in our data, how can we do this? Let me first introduce you to the traditional approach, some traditional model, and then I will present some problems about this model and how we improve this model and some algorithm and then some experiment that we have done. There are several papers about finding periodic patterns in data. Some of the papers, the traditional definition is by Tambir and al. It is the following. Let me explain to you. So the input is a transaction database, some database like what the people buy in a store. It is a set of transactions. So here we have 10 transactions, what the people have bought. So the first transaction is some items, some products the people buy, like A, B, C, E. A may be for apple, B for bread, C for cake, E for eggs. And then transaction 2, A, B, C, D, then A, B, E, and so on. So all these transactions are ordered by time, maybe. So the first one is the first transaction, then number 2 is the second one, and so on. And by looking at the time in the database, it could be the time like this, 1, 2, 3, 4, 5, or it could be the times in terms of minutes or hours when the people went shopping. Then by looking at this time, we can find that something are repeating in the database. So for example, if you look carefully, A and E appear many times. Not so many times, actually 2 times. But some other like B and C, B and C, B and C, B and C, and so on. So maybe it is some patterns that is periodic. Okay. So in the traditional definition, what we call periodic frequent pattern mining, the user has some data like this. Okay, it could be shopping or other kind of data can be represented like this. And then the user has to set a minimum support threshold. That means a minimum frequency. So for example, the user can say, I want to find all the patterns, the set of items that are purchased together at least 4 times. So that would be the minimum support, minimum frequency. Also, there's another parameter, the maximum periodicity. That means if you set to 1 week, it means I want to find the patterns always repeat at least every week. Never more than 1 week. Okay. So let me show you some example what will be the result. The output is all the sets of items, we call the periodic frequent item set, some set of items like BD, that have a support, that means appear at least some minimum number of time, and have a periodicity that is not greater than some maximum periodicity. It is a value set by the user. So for example, if we set minimum support to 4, and maximum periodicity to 3, we find the result in the table below. So what does it mean? Minimum support to 4. It means we want to find some set of items appear at least 4 times in the database. So for example, B is a frequent item set because it appears 8 times. It's more, at least, more or equal to 4. And the maximum periodicity means we want to find some set of items that never appear for more than 3 days later or 3 weeks later, for example. So for example, here B has a periodicity of 2 because B usually appear at least every 2 transactions. Never ever it will appear after more than 3 transactions, for example. So we say that B is periodic. Okay, so this is the traditional problem definition. So to give you more details about this, in the traditional problem, we measure the periodicity of an item set using what is called the period. It is a concept. The period of an item set, a set of items, is the number of transactions between two consecutive occurrences of that item set. So for example, I will explain this with an example. The periods of BD are the following. Okay, if you look at the database on the right, I have highlighted all the occurrence of BD. And now the periods, it will be the time between each time that BD appear together. Okay. So first, BD appear in transaction 2. This is a special case. It is the beginning of the database. We never saw BD before, so we say 2 minus 0. We assume maybe BD was there before, but we don't know. So we say the period here is a 2. Okay, because BD appear after 2 transactions. Now next, BD appear again in transaction 5. So we say 5 minus 2. The period is a 3. There was 3 transactions between these 2 occurrences of BD. So 2 and 3. Now BD appear in transaction 7. So 7 minus 5. It is 2 transactions later. So we say this period is a 2. Now we continue. We find BD again 2 transactions later. And finally, it is the end of the database. This is also a special case. So here we say there's 1 transaction after BD, so we say the period is 1. So the period of the item set BD are 2, 3, 2, 2, 1. So what does it mean? This means this is the time between every time we see BD. The first time there was 2 transactions, then 3, then 2, then 2, then 1. Okay, so in the traditional problem, they want to find the maximum period of the item set. So for BD, we look at the maximum between 2, 3, 2, 2, 1. The maximum is a 3. Now, in the traditional problem, they say that an item set is periodic if the maximum is never greater than some threshold set by the user. So if the user say the maximum is a 3, then BD is periodic. But if the user say the maximum is 2, BD is not periodic because at least one time the period was more than 2. So it will not be periodic. Okay, so the traditional problem of periodic frequent pattern mining, there have been many algorithms or work on this topic, but there are 2 important limitations we explain here. So first, an item set is discarded as non-periodic if it has a single period of length greater than the maximum periodicity threshold set by the user. So that means if the user say the maximum periodicity is 1 week, if the pattern only one time appear after 9 days, for example, a little bit more than 1 week, then it will not be periodic, and the traditional algorithm, they will discard this item set. They will not show to the user. So we think that this is too strict, because maybe a pattern is always periodic, but only one time is more than the maximum. Another problem is that the prior work, they only consider whether the periods are less or more than the maximum periodicity, but they don't care about how big the difference is. Okay, so let me show you some example here. I draw some picture. Here we have the maximum periodicity, the line here, and we have the time. The y-axis is the periodicity, and the x-axis is the period. So here the periodicity is lower than the maximum, then later still lower, and then we exceed a little bit. Now in the traditional problem, that would be enough to discard the pattern. It's not periodic. But also later maybe we exceed more by a lot, the maximum. But for the traditional algorithm, if you exceed just a little bit or a lot, it is considered as the same thing. But in real life, it's not the same thing actually, to exceed a little bit and so on. So it's not very flexible. So our solution, we define a new problem in this paper using a new measure for the periodicity we call the liability. The idea is like that. We have also a maximum periodicity, but we allow to exceed. So we say the pattern sometimes can exceed a little bit. And also even sometimes can exceed a little bit for a few periods in a row. But it must not exceed by too much. So we will accumulate by how much we exceed. And if we accumulate too much over time that we exceed, then we say it will not be periodic. So this will be more flexible. So let me explain this in more details to you next. Okay, so we want to find some item set that have a stable periodicity. Usually will be periodic, but it will be more or less stable. Okay. So we define the liability of an item set as a new measure called LAX, the liability of X. It is the cumulative sum of the difference between each period and the maximum. So we have the maximum, let's say 1 week, and if we exceed 1 week, then we accumulate by how much we exceed over time. And if we accumulate too much, we say it is not periodic. That's the main idea about this. Okay, so here I show you an example with B and D together. So we have the period we calculated before. They are 2, 3, 2, 2, 1. And we say the maximum is 2, for example. So here I will not show the formula exactly, all the details about calculation, but I will just explain with an example. So the liability of X, the first liability of X, for the first period is a 2, okay. So the liability of X for the first period of 2, it is the maximum of 0, and 2, because we have 2, minus the maximum, by how much we exceed. So 2 minus 2 is 0. We did not exceed the maximum. So we say the liability is 0. Now, the next period is a 3. So we say liability of X for the next period. It is the maximum always of 0. And the liability of X for the period before, what we calculated before, okay, for 2. So this was 0 here, plus the difference between 3 and the maximum. So 3 minus 2 is 1. So the maximum of 0 and 1, it will give you 1. So here, for this period, we have exceeded the maximum a little bit by 1. So we will accumulate the 1. Now we move to the next period over time. We continue over time. Next period is 2. So here, the liability for the next period will be the maximum again of 0. The value we had before, which is 1, plus 2 minus the maximum, because we had 2. So 2 minus the maximum is 0. The maximum of 1 and 0 will be 1. So here we did not exceed the maximum periodicity, but we accumulate, we keep what we have accumulated before. It was 1, so the result is 1. Then we continue with the next one and so on. And at some point, the liability is reset to 0. So the idea is here, why we do maximum with 0 and the liability before? We do maximum with 0. The reason is because we don't want the liability to become negative. So if the liability become negative over time, it will be reset to 0. So we only care about by how much we exceed the maximum, but we don't want to have negative value. Okay. So now we say to calculate a pattern is stable or not in terms of periodicity, we do the maximum of the liability. So here, among all the values, 0, 1, 1, 1, 0, the maximum liability is 1. So that means usually this pattern was stable. Sometimes it exceeded the maximum, but not always. So we consider it is an interesting pattern and we will show it to the user. Okay, so the new problem we define, now I give you the more formal definition. We want to find all the patterns we call stable, periodic, frequent patterns. What is this? We say an item set X is a stable, periodic, frequent item set if the support is greater than some minimum, the frequency, for example, it appears at least 4 times, okay, and the maximum liability is smaller than some maximum. So totally we have 3 parameters: the minimum support, the maximum periodicity, and the maximum liability. So the main difference between our new problem and the traditional problem is that we are more flexible. We are not very strict, but we allow to exceed the maximum periodicity a little bit for some period of time, but it must not be for too long and not by too much. then we still keep the patterns, so it will be more flexible. Okay, so now if we want to find the solution to this problem, we want to find all the stable periodic problem. It is some problem where there's always only one solution. So we need to design some algorithm to find the solution as quickly as possible. So to do this, we don't want to look at all the possibilities. So there are a lot of possibilities like A, B, C, D, E, then AB, AC, AD, AE, then BC, BA, and so on. So A, B, C, D, and so on. So to avoid looking at all the possibilities, we define two properties in the paper. The first one is well known. The support of an item set X is anti-monotone. I will explain to you with an example. And the maximum liability is monotone. So let me explain this with the example. So if we have the support of an item set like BD, maybe it appears 4 times, maybe. Then we know that the support of any superset of BD, like BDE, BD we add something like BDE, then any superset of BD cannot have the support greater or equal to that of BD. So if BD appears 4 times, then BDE cannot appear more than 4 times. So we can use this to reduce the search and do some efficient algorithm. But what is new in this paper? We prove that the maximum liability is monotone. So if BD has a maximum liability of 3, for example, we know that all the superset of BD, like BDE, cannot have maximum liability smaller than 3, for example. It must be greater or equal. So this is interesting. We use this to do some efficient algorithm to find all the patterns, and we don't need to look at all of the search space. So how to find the patterns? We define some algorithms. In this talk, I will not explain the details of the algorithm. The algorithm is called SPP-Growth. If you know about pattern mining, it is based on the FP-Growth algorithm. It is a very famous algorithm. So here we have changed the FP-Growth algorithm to find the stable periodic pattern. So to do this, we do something a little bit different. It is a little bit changed, and then we can find what we want. So the first step, I will just say briefly, we look at the database and we count the support and the maximum liability of all the items A, B, C, E, and D. Then from this, we will eliminate all the items that have a support that is smaller than the minimum support. Then after that, we will do like in FP-Growth. We will build a tree from the database like this. So this tree, called the SPP tree, will store all the data from the database. And then we don't need the database anymore. We'll look at this tree to find the solution. Okay. So I don't want to explain the details. If you want to know more, you can also have a look at the paper. So again, I will skip these details here. So the main difference with an FP tree in the FP-Growth algorithm and our algorithm is that in the tree we have the timestamp like 1, 6, and 8. That means E here appear in these transactions here, 1, 6, and 8. So the algorithm is a little different. Okay, so I want to talk to you about the experimental evaluation. We have 4 databases. The first one is some synthetic database. The second one is about mushroom. It's not really relevant for periodic pattern, but it's just to test on different kinds of data. The third one is about the click on the web page. And the fourth one is more interesting. It's about shopping. What do people buy in a supermarket? So all these databases have different characteristics to see how the algorithm behave on different kinds of data. So first, we did some experiment to evaluate the runtime of the algorithm. So what we did, we evaluate the runtime for the mushroom, the other database, and all the database. Here I just show 2 of them. And we test our algorithm with different parameters. So here we change the maximum liability parameter, and we have different lines to indicate different minimum support, maximum periodicity. So what we find out, if we increase the maximum liability, it will increase the runtime. Here you can see. And also if we increase the minimum support or the maximum periodicity. So this is quite obvious. And it makes sense actually. It's not something surprising. I want to say also we did not compare with the traditional algorithm for periodic pattern mining. The reason is that it is a different problem, so we cannot compare it directly. It will not be fair. Okay. We also look at the number of patterns found. So again, we change the maximum liability, the minimum support, maximum periodicity, and we count the number of patterns on the mushroom and the other database. And we find if we increase the minimum support, the maximum periodicity, the maximum liability, it will increase the number of patterns that we will find. So this also not something really surprising, it's something we expected. We also look at the memory usage. We compare different values for the parameters, and we find when we change the parameters, the memory usage will change. Also, this is something we expected, because if we increase some parameter, we need to look at more patterns in the search space. It takes more time, spend more memory. Now, what is more interesting is some patterns we found in the real data. I want to talk to you about this. So here we look at three sets of items. Box. We have the periods of box. Box is in blue here. And here we have the periods. We have the periodicity on the y-axis, and we have the maximum periodicity. We set the maximum periodicity, for example, to 5. I think it's 5 months or days. And we see that box is always below the maximum periodicity. So the periodicity of each period, here is a 3, here is like 4, and so on, always below the maximum periodicity. So this pattern is periodic, even if we use the traditional algorithm. Now, if you look at cake and heart and vintage, another set of products, the red line, here is periodic, below the maximum, but here it exceeds a little bit, then is below again, exceed a little bit, then below again, exceed a little bit, and so on. So this pattern is interesting because the traditional algorithm will say it is not periodic. But here in the chart, we can see that this pattern is quite stable actually. So using our algorithm, we can find it. Because we allow to exceed the maximum periodicity a little bit sometime, but overall, it must be almost always periodic, so we keep it. So this just to show we can find some patterns other algorithm cannot find. So in conclusion, in this talk, we presented a new type of patterns, the stable periodic frequent patterns. We had a new measure, the liability, to find these stable patterns, and an algorithm called SPP-Growth to find this quickly, using some new pruning property. For future work, there's a lot of possibilities to do. We could look at other type of data, do faster algorithms, and so on. If you want to try the algorithm, you can download the source code in the SPMF data mining library. The source code is free. Or if you want to apply on your own data, you can also apply on your own data. Or you can also, if you want to do research on this, you can change the algorithm, add some new features, write some new papers. All the database, all the code is there to do your experiment if you want to use it. The software is in Java. It is easy to integrate also in other software that are not in Java. You can connect it from the command line and so on. It uses the text file, very easy to use. So that was all for my presentation. I hope you enjoyed this little video about this. And if you want to see more video, you can go back to my website. There are more video like this to explain some algorithm. That's all.